Okay, all right. So let me see where I was starting at again. Okay, right. So previously, with everything that Greg taught us, it was all entirely DC circuits. So just a really quick recap on that. If I were to draw a simple graph, so if I were to draw like this, so the vertical line is our voltage. I'm just going to do +1 there for positive 1 volts, -1 there for negative 1 volts. And then the horizontal line is going to be our voltage over time. For DC, it's always going to be a constant voltage. But with everything that we're learning now with AC, rather than it being a constant charge, it starts at 0, it goes up like so, hits its maximum voltage, curves back down, hits 0, it continues going into a negative charge, hits its peak negative value, and then returns back to 0.
All right.
So, and what happens with your AC circuits is this is happening literally for our electrical systems here in the United States. This is happening literally 60 times a second, where it's going to a positive charge from 0 all the way down to a negative charge and then back to 0 again.
Okay. Okay, I'm following.
And the right, so one of the three key terms for that is frequency. And that is the cycles per second. And it's measured in hertz. And basically one cycle is the voltage basically doing this. It's
Okay. So it's one sine wave?
yeah, this is yeah, the AC voltage, the actual voltage is literally following a sine wave. So this one cycle right here.
Okay.
So that's your key difference. Let me go ahead and move up to the next one. Covered that. Right, so a couple differences, other differences between DC and AC here is that AC generally, most applications, it's more energy efficient in just about all of the applications, which is why you've got it in pretty much any place you're going to be working in, or even just in your own home.
Right, right.
It's also easier to step the voltage up and down as well versus DC.
Okay.
Let's see. Right. So one thing that's going to be different with AC is all of the formulas that Greg gave us before relating to DC voltage, current, resistance, all that stuff. Not all of those formulas will be usable with AC. So one important thing for AC power is if you need to determine the power loss, normally, to get the power consumed, you just take your voltage and multiply it by your amperage. But with this, that formula does not work. So your power loss specifically for AC is going to be your amperage squared multiplied by your resistance. And you'll need to do that. You'll need that formula for at least one homework problem. You might need it for more. And that's just for this assignment.
All right, I get it. AC.
Okay, so one other new thing with AC circuits, and I'm pretty sure there shouldn't be any questions with calculations on them, but there are going to be some questions relating to this on the homework assignment. There are these things called eddy currents that you'll get in the wire for an AC circuit. And if I were to basically draw the cross-sectional area of a wire, in a DC circuit, the electrons would be pretty evenly spaced out throughout the wire, like that. You know, basically the little circles would be like the electrons passing through the wire.
Okay.
But with an AC circuit, when the current is alternating back and forth, when it shifts back and forth between the positive charge and the negative charge, it generates what's called eddy currents, and it basically produces resistance inside the wire itself. And it also causes this thing called the skin effect, where instead of having the electrons moving, pretty evenly through the wire, they start to concentrate around the edges of the wire instead, like this. And as a result, it actually raises the effective resistance of that wire, since all of the electrons are being forced into a smaller cross-sectional area.
Okay, that makes sense.
And the higher the so the higher the frequency is, the number of cycles per second, if this is alternating back and forth faster, this effect will become more severe, and you'll actually get even more resistance.
So does that mean they'd be like closer to the edge?
Yeah, it would most likely force them closer to the edge, and as a result,
Okay.
it would raise your resistance even more in the wire.
Okay, I gotcha.
But yeah, those are two important things. It's eddy current, which produces this skin effect. No formulas for that yet, but I'm sure we'll have something later on in one of the other assignments. Yeah, this is going a lot quicker than last time. I've got my, my paper here from the last session to draw off of. Okay. Oh, I think somebody just joined in.
What up?
Hey, all right.
Stella.
We're probably like a third of the way through everything that we covered in the last stream.
Yeah, all the shit.
This is going
that
a
I
lot
lost.
quicker now that I've got that paper from last time to draw off of.
Hell yeah, bud. I have questions.
Okay. Let me finish going over all of this, and then we can go over your questions.
Yeah, no worries. There's a couple things that you didn't touch up on.
Okay. Yeah,
yeah,
I kind of
so-
I tried to skim over what I thought were the important bits, but yeah, I'll take care of whatever questions you've got at the
Yeah,
end of
dude,
this.
no worries. You keep doing what you're doing. I'm taking notes right now anyway.
Okay.
So I just figured I'd pop in and listen while you were, doing what you were doing.
Okay, cool. All right, so when Roland had his stream, I don't know how much of it you saw, but he had a drawing of a generator. And I'll do my best to try and redraw it here. So inside of the generator, you effectively had a magnet on one side, and it had the north side of the magnet sticking in towards the center. And then on the opposite side, you had another magnet. And that one had the south end of the magnet pointing in. And what this does is it basically creates a flux field, basically that, the magnetic effect.
Right.
Where you've got these flux lines going in the direction from the north over to the south. And inside of that space between these two ends of the magnets is you've got this this piece of wire. It's basically spinning either clockwise or counterclockwise inside of there. And what happens is, as it's actively spinning, and these wires are actively moving through these flux lines, it generates that voltage through the wire, which as a result produces the current. And that voltage is going to be exactly the same as this sine wave right here. So as it spins, it's going to start at 0, and then, right, let me draw this real quick. Okay, so this is at 0 degrees. When it gets to 90 degrees, 1/4 of the way through, it's going to hit its maximum positive voltage. And then as it continues and reaches 180 degrees, it's going to reach back to 0. And then at 270 degrees, it's going to hit its maximum negative. And then at 360 degrees, it's going to reach back up to 0 again, and then it's going to repeat that cycle all over again.
Okay.
And if you were to take, actually, let me give you the formula first, which is, where did I put that formula? Here it is. Okay, so if you want to find the specific voltage of your generator here, you can use this formula. So your voltage E is going to be equal to E peak. E peak is basically your peak voltage.
All right.
And that's going to be multiplied by, oops. It's going to be multiplied by the sine of your angle. So a little thing is, if you take your calculator right now and you just put in the sine of, say, 90 degrees, it would actually come out to 1. And then if you put sine of 180, you'd get 0. Sine of 270, you'd get -1. So you're basically taking the value of this graph and then just multiplying it by your peak voltage.
Okay.
So what I have here, this is literally a graph for the sine of theta. It ranges from +1 to -1 if you start punching the numbers into your calculator. Okay, so we covered that. Right, so one other key term which you might need is the cycle. And that is 1 rotation in a generator. 1 rotation in a generator, or, which is basically just the amount of time it takes to, do one of those. Okay, and then another formula that you'll be needing to use, another term and also the formula. Okay, so you're also going to need to know what the period is, and that is the amount of time that it basically takes for one cycle, one of these, to complete. Period specifically is going to be equal to 1 divided by your frequency. I don't know if that handwriting is too small for you to see on the webcam or not. You able to read that?
Not really. I could see the formula above it.
Shoot.
Okay, yeah, I see that.
You can see it from there?
Yes.
Okay. Am I going to get myself a better webcam? All right.
Just if you had not smart people handwriting, it would probably be like way bigger, and you know, us stupid people write very large. Um, ah man, if you had a stylus and could fuck with Microsoft Paint, it wouldn't be a terrible idea to try doing this on that.
That might work. I don't have a stylus, though.
See, I was thinking about maybe screen recording my phone because I have the Note 10 Plus,
Mhm.
and I can take notes with my phone, like handwriting notes and make drawings and all that shit. And I have a screen recorder that I could record audio with. But the thing is I'm not smart enough to do this.
Is my mic echoing?
Not for me, no.
Okay. I just see feedback whenever you guys talk.
Yeah, no, I get echo from both of you, and I'm always under the assumption that it's me because I have inferior internet. I'm sorry, I interrupted. Nate, please keep going.
Right. So, okay. So, couple other things you'll need to know, at least for just this one lesson. A couple of key terms. Your peak is going to be the distance from 0 up to here. That's your peak. You might also need to know your peak to peak value, which is literally just the difference between your positive and your negative peak.
All right.
And then there's two other things. There is one called your RMS. And RMS specifically is short for root mean square. And it is the exact same thing as what they also refer to as your effective voltage, which you can just write it as E with a little EFF in front of it.
All right.
And basically what your effective voltage is basically if you took it's basically taking your AC voltage and rewriting it as your equivalent DC voltage. And there's a formula for that. And your effective voltage is equal to your peak voltage divided by the square root of 2.
All right. I got that.
And it looks like, I think there's just one more thing I need to cover here. At least one thing from my notes, anyway. Okay, so there are these things, they're called full wave rectifiers. And what they do is they actually alter the voltage for your AC. And what it does is instead of having your voltage alternate between positive and negative, what it does is effectively this. instead of going down into the negative when it hits 0, it just goes right back into the positive again.
Ah.
And there's one other type of rectifier. And to be honest, I forgot the name for it, but there's another type where when the voltage goes back to 0, instead of going into the negative or even just going back into the positive, it simply stays at 0, where there would have normally been that drop down into the negative.
Single wave rectifier.
Yeah, single wave rectifier. This is what a
Okay.
single wave rectifier would do. Your voltage would go up into the positive, hit its peak, go back down. It would stay at 0, where it would normally go into the negative, and then when it gets to that point where it would start rising back up again, it does so like that.
Okay. Interesting.
It's full wave. And then there's single wave. And there is another formula. There's a formula for full wave rectifiers. So if you want to get the effective voltage for something like this specifically, there's a different, or sorry, actually. No, sorry, this is for your average voltage. There's a formula you'll need to use, which is, so that's EAVG, your average voltage for a full wave rectifier. It is equal to 2 times your peak divided by pi.
And that's for the average voltage?
Yeah,
you
that's to
said?
get your average DC voltage value when you've got your AC voltage going through a full wave rectifier.
All right.
And Tyler, you said you had some questions?
Oh, my dude. Well, I made a 64.29 out of 100 on the test.
Right.
And
Which
I
ones
feel like
did you have trouble with?
Oh, bro. 44 through 54, I missed, and I'm 100% that it has to do with wording, because I wrote down everything that you have on your page. But like, hang on, let's see. Right now, I'm taking notes. What I do is I take the test, and then I go through and I write down like everything. Since we can use notes on tests.
Mhm.
So hang on real quick. Let me just mark my place. Okay. I've gotten to 33. So let's see here. Okay, so let's hang on. I'm looking for math stuff. Give me a sec.
Yeah, pick one question and then I'll show you the process for it.
Yeah, I'm trying to pick a difficult thing, which is probably not even that fucking difficult. Sorry, my internet has just now decided that it doesn't want anything to work. Let's see.
Are you on like your phone hotspot, or did you get internet at your place back?
I got internet at my place back, but I'm on the internet. My brother's on the internet. He's streaming on Xbox Live. My mom is on
Oh,
her
yeah, that's good.
phone and her tablet, and my dad is on his work computer and his phone. So I basically have dial-up right now.
Oh yeah, man. I know how it is. I know. exactly.
So like, yeah, okay. There are a lot of things, like question 44, when it talks about peak voltage. There are specific values, specifically like if we're looking for EFF, it's equal to E peak times 0.707. That wasn't something you went over. Like if we have our peak voltage, which is 170 volts, how do we find the effective voltage?
Right. So going back to right here. So this formula here, where your effective voltage is equal to your peak divided by the square root of 2. Square root of 2. Square root of 2 is the same as. Let me just double check and make sure I'm doing this right. Oh, that's
Where the fuck is my calculator? Here it is. Let's see. So we have.
right. So I'm gonna take this and I'm gonna rewrite this really quick. So your peak voltage over the square root of 2 for getting your effective voltage. This, I'm going to rewrite it here. It's still going to be the same exact thing. This was basically the same as saying 1 times your peak over square root of 2, right? Same thing?
Right. Yeah, same
Okay.
thing.
So if I were to rewrite that again, so this could also be rewritten as, say, 1 over the square root of 2 times E peak. This is also the same as this. 1 over the square root of 2 is equal to 0.707.
Right, which is that they just give it out like they just have done that math already, is what it is.
Yeah.
And so that tripped me up as to when I should use the formula that you've given me.
Yeah,
And
so
it's because of their wording.
So you know what? This formula that I gave you guys originally, you can actually just throw that one away because there is actually a simplified version of that. So yeah, your
Yeah, which
your
is
effective voltage is
yep.
going to be equal to your peak voltage multiplied by 0.707. That's your simplified formula right there.
That's how the lesson wants us to do it. But you are right in the square root of 2, because if you read the material, it says originally in the text, E peak over square root of 2.
Mhm.
Bro, how are you drinking a Monster at 8 p.m.?
I don't have work tomorrow, so I can stay up pretty damn late tonight.
Oh, you dick. You're such a jerk.
You gotta remember, I'm out of work right now, so I've literally just been sitting around at home all day.
I'm sorry. That would kill me.
No, dude. I'm
I
sure
got
he's
stuff to
making
kill
more
time.
money than he was when he was working right now. Right?
Sorry, what was that?
Said I'm sure you're making more money now than when you were working, right?
Probably.
You're
I haven't
getting that
checked yet.
600 and then your unemployment.
Which is like 325, right?
Yeah, something around 300.
Something like
Yeah,
that.
I just got my first unemployment this week, which is weird because I'm still working. So I'm
What?
not really sure. I'm not really sure how they pulled that.
I hate you. Oh man.
Anyway.
If I knew I was gonna keep my job after the furlough, I would have taken the furlough. But I hate sitting at the house, so yeah.
Yeah, no, I understand. I'm sure it could get tiring after this long.
Yeah.
What was another one you had trouble with?
Let's see. Same deal. The effective voltage is 480. What's the peak? And they use that different formula. And I have here
Which
when I was
problem?
asking. This is problem 45. The next question. Yeah.
Oh,
And
okay,
it
yeah,
gives
so-
you a different formula. So,
Oh, definitely.
I'm trying to equate what you've shown me to what they're showing me, and that's what
Oh, okay.
like
Let me explain that to you. I can explain this part to you real easy. Okay, so for this problem, they give you the effective voltage, right?
yeah,
So your effective voltage, which is
480.
480,
Yeah.
is equal to your peak voltage times 0.707. So basically, the reason why you're seeing it is this. Let me just show you here. So if you took both sides of this equation, you divide both of them by 0.707. I just use my other side of the paper here.
Right, you're just doing the math and you'll get 1.414.
0.707 is equal to E peak. So 0.707, if you took 1 and divided it by 0.707, you'll end up with 1.414.
Yeah.
And that's why they were saying it. So it's basically just the inverse of this, where
Yeah, so if you're trying to find E peak,
yes,
E peak is equal to E effective voltage times 1.414.
yes, exactly like that.
Yeah, like now that I see the mistake, I feel fucking stupid.
No, it happens.
Let's see. 46, I completely understand why. I just looked too into that. And the rest of these are E peak and E effective, and just when you apply the when you apply the formulas. That's what all these are.
Yeah.
So really is just not applying the formulas correctly, and that's because of the wording of the problem and my lack of information on my formula sheets. So, yeah, I understand now. It's
Okay,
stupid,
cool.
but I get it. Thank you for clearing it up. I really appreciate it.
Were there any other ones you had trouble with?
I mean, besides my whole life.
Is that Golden Bob sheet the one where you're getting the majority of the formulas?
Nah, dude, this shit's in the chapter.
All of my formulas for this stuff is just it's just the stuff that Roland posted online.
Oh, okay.
So I just basically whenever I start working on an assignment, I just try to skim through it and I look for key terms and what they are and like how they relate to each other, and then I also look for relevant formulas that are posted in there. Is what I try to do
Okay.
just to get like the gist of stuff figured out.